purpose of this video is to go over number 11 on the spring 2014 final. And the point of this question is to see if you can get an understanding of what it means to have a limit at a point in behavior, differentiable or not. So the first kind of setup, you can see the answer down here, but to start this problem, you just want to first look at the first condition. It's defined everywhere except for x equals 2. So if you go to start that, you have your graph and you put x equals 2. So you know there's going to be a point of discontinuity here. And there's various ways to do the point of discontinuity. So that meets that condition that I have to have some jump or something going on at x equals 2. Then the second thing is the limit at minus infinity and infinity is going to 0, right? So the limit as x goes really large goes to 0, and as x gets really large negative, it goes to 0. So I have kind of two choices here. It can approach 0 from the top or the bottom, and depending on the setup of the problem, I don't know which one's going to happen at that point, but as long as it's going to 0 from the left and to the right, it's going to meet that condition. The third condition has to do with a point of discontinuity. So here it says the limit on the left goes to infinity, and the limit on the right goes to minus infinity. So somehow I have to connect these arrows in a way that's going to work out. So you can see this one's not going to work here, and possibly just to see what's going on. I mean, I guess it could do something like that. So as long as I go to one of these arrows, I'm going to meet the condition on the right and the left. That one's satisfied. The third one is saying the first derivative is less than 0. The first derivative is slope. So from x is less than minus 3. So 1, 2, 3. At x equals minus 3, maybe I can kind of extend this out here. At x equals minus 3, my slope is negative. And my slope is negative for x being greater than 5. Right? So my slope has to be negative at from this point on and this point on. So I'm not for sure exactly how I'm going to connect them yet. I just know that has to meet that condition. F of 3, the derivative at 3, and the derivative at 5 is 0. So that means there's a maximum or a minimum there. Looking at this thing, multiple solutions, multiple ways to kind of come about it. I know that I need to have a maximum or a minimum here. So I have to approach the 0 as x goes to minus infinity. So trying to, see something like this, I know my slope has to always be negative here, so I'm not going to be able to do that. I have to do something like, the answer here. So you can see if I smooth this out, I have a negative slope here. I always have a negative slope. I'm approaching minus infinity. As x goes from minus 3 to 2, we don't know anything about the slope, but we know it has to approach positive infinity as it gets closer and closer to 2 on the left, right? So it's looking a little rough, but we can always smooth it out. And basically, we get a minimum there. I'm doing the same thing on 5. Right? We can do something like this, because we know we need a negative slope. This is a negative slope from x is greater than 5. And this is a point of discontinuity. On the exam, I believe it was exam 3. Exam 3. I did one very similar to this. Open the answer key here. And it was maybe a little easier because I gave you this little table for the second derivative as well. So that gives you if it's concave up or concave down. So the limit as x goes to minus infinity at the function as x goes to minus infinity is 3. So that tells me I have to approach this horizontal asymptote. Sorry, this program's going crazy. That tells me I have to approach that. That is this condition. The limit as x goes to positive infinity meets this condition over here. And so you just go through and put together the different pieces and then connect the dot. And a lot of times there's more than one example that could fit. Just make sure that you meet all the conditions. So hopefully this video helps. If you have any questions, please let me know.